teaching of Padova, collaboration with the observatory. So the main results are published in these 4 papers that you can see here, even if there is some ongoing work. And it was done, of course, in collaboration with my supervisors, Bianca Poggianti, Marco Guglieldi, and Alessia Moretti, and as a part of the GASP collaboration that I will introduce that, so in collaboration with the whole team, essentially. So the title is Star Formation in Young Stellar Clumps of Pressure Restricted Galaxies as seen by HST. So now we'll give you an introduction of all the different parts that are summarized also in the title. So let's start with the stellar clumps. So we've known, and especially in the last decade with many HST surveys, we know that star formation in galaxies, and especially in disks, doesn't occur evenly distributed in the galactic disk, but in these clumpy regions that we call stellar clumps. So in the Milky Way, we can see them resolved, we can see the single stars, etc. But when we move far away from the Milky Way or from the Andromeda galaxy, we see this ensemble of stars as single objects. They're very important because they are the smallest structures in which we can assume the IMF of the stars will be well sampled, and so we can treat them as stellar populations and study their age, mass, etc. And they are found not only in galactic disk, as in this example from the FANGS collaboration, but also in irregular starburst galaxies, high redshift galaxies. This one, for example, is an irregular galaxy from the LAPS sample. And so it's interesting to study if the clumps have different properties depending on the properties of the galaxy itself. And this is where our work is focused. Clumps are also very important because they can affect the morphological evolution of galaxies, because, for example, if a clump can survive for long time scales, it can sink because of the dynamical friction towards the center of the galaxy and contribute to the formation of the bulge. While if the evaporation or the disruption of the clump is very efficient, the contribution will be mainly to the galactic disk. About the formation of clumps, there are many observational studies, simulations, also analytic models that essentially predict that the formation of clumps occurs in the densest regions of the molecular gas clouds. So the model, the idea essentially is that the neutral medium collapses and condensates into molecular clouds. And in the densest regions of these clouds, we have the formation of the clumps. It's a turbulent free cascade, so completely scale-free, and the footprint of this process should be in the mass function of very young stellar clumps before they start evolving because of their dynamics, or in the mass function of the gas clouds, and should be well represented and well described by a single power law with slope -2. So essentially a lot of small and low mass clumps and clouds, and just a few very massive clouds and stellar clumps. So, as I said, also the second part of the title was in pressure restricted galaxies. So this is the peculiar environment in which we want to study these clumps. And galaxies undergoing pressure stripping are peculiar galaxies that we find in galaxy clusters. And essentially, when a galaxy is accreted by a cluster, the environment in which it is embedded changes from the intergalactic medium to the intracluster medium, which is denser and hotter. And under certain conditions, the effect is the stripping of the interstellar medium. You can see an example sort of here, in which in blue you have the stellar disk of the galaxy with this red emission, which is molecular gas. So you can see that the disk is essentially undisturbed because pressure stripping is an hydrodynamical process that doesn't affect the stars. But the gas can be stripped and forming these long tails. Indeed, these galaxies are also called jellyfish galaxies. And we see that it is an hydrodynamical interaction and not, for example, tidal effects, interactions with other galaxies, because the stellar kinematic, here it is a Muse map, is essentially undisturbed and very similar to the one that we would observe in an isolated disk. Interestingly, if we look again with Muse, but focusing on the H-alpha emission, so the ionized gas, we see that the emission comes not only from the disk, but also from the tails, and not only diffuse, but also clumpy. And the line ratios of these regions suggest that this ionized gas is essentially ionized and powered by massive stars, not by AGN, not by shots. So essentially, we're looking at ongoing star formation in this peculiar environment because we are far away from the disk, the gas is stripped, we are embedded in intracluster medium, so it's a very peculiar environment in which we can still form stars. However, this resolution is not enough. It's about 1 kiloparsec, and this is one of our galaxies, and that's why we wanted to observe them also with HST. Another reason to go to a better spatial resolution is the study of the morphology of the clumps in these tails, because there are previous studies focused on like tens, dozen of objects, in which you can see also here, for example, there is a very compact H-alpha emission with a UV emission that, apart from the different spatial resolution, is characterized by this diffuse tail pointing towards the disk. So the idea essentially is that the ICM is able to push the gas cloud far away from the disk, and essentially, if the cloud starts in position 1 and forms new stars in that position, the effect of ramp ratio stripping will move the cloud in position 2, leaving the stars, the red stars, in position 1, and so on and so forth. And so we should have this correlation between the distance of the stars and their age, the distance of the stars from the disk and their age, in which we have very young stars far from the disk, while the old stars are the closest. And that's what we see here, because H-alpha is tracing very young stars, while UV emission is tracing young stars, but not only, let's say, not so young. And now I will go in detail. So essentially, there should be this correlation between the age and the spatial distribution of stars. So about our observations, we observed the 6 galaxies that now we'll show you from the GASP sample. So a survey of jellyfish galaxies, mainly performed with MUSE. So we went better in resolution from 1 kiloparsec to 70 parsecs, and we observed them in these 5 filters. So these 2 UV band filters are very useful to discriminate the age of the stellar population. You can see our spectra of different ages, 0.01, 0.1, and 1 gigahertz. So the UV slope changes a lot because we are losing massive stars. But also with the other optical lines, optical bands, we can collect the emission coming from the H-alpha, so tracing very young stars. So we can have essentially an idea, a map of star formation on 2 different timescales, because the H-alpha is tracing stars younger than 10 megayears, because we are tracing the gas ionized by the most massive stars that we can form. While in UV, we are tracing stars younger than 200 megayears, because we are tracing also stars that are less massive, but still quite bright in UV. Not enough to ionize the gas, but enough to be observed in the UV. And these are the galaxies. So you may recognize this one, which is the one that I showed before. And now maybe you can see that the resolution is much better, and the clumps are not just blobs very round, but we can see the morphology of the object in blue. So again, the stars that are bright in the blue bands. And also we see the older populations in the disks. So the idea is to detect the clumps and compare them with the samples that we have in literature for isolated disks and starburst galaxies. The clumps are detected with astrodendron, both in H-alpha and UV. Here you have an example for GO201, which is the one that was on the top left. This is the H-alpha image. And the clumps are divided in 3 categories. You can see the orange, red clumps. The colors is tracing if we have substructures inside the larger clumps or not. And these are the disk clumps, because looking at the RGB images, they were looking undisturbed. So they are experiencing the effect of ICM, but they are not formed from stripped gas. The blue clumps are in the extraplanar region, so we are still inside the optical disk, but from the RGB images, they were already showing like asymmetries, elongation, so they were most likely formed from gas that is already being stripped, but because of projection effects, still inside the optical contour of the galaxy. And in green, everything that is outside the disk, so by definition formed from stripped gas, and these are the tail clumps. We have also a third sample of objects, which are the optical star-forming complexes. So we ran astrodendron on the optical images, and you can see the results here in the violet contours. We could do that only in the tails, because we are far from the optical disk, we are not contaminated by the disk, and they are important because we are essentially tracing the whole stars that were formed from the stripped gas. And essentially, they were selected by keeping only those that contain at least one UV or H-alpha clamp that you can see as a purple or gold contour. So we have these 3 samples, and these are the numbers of the sample. This is the first, at least to our knowledge, statistically robust sample of clumps in this kind of galaxies. We have 2400 H-alpha clumps and 3700 UV clumps. Most of them are in the disk, but there is enough statistics also in the other regions. And we have more than 400 complexes in the tails. An important cut, if according to what we want to study, is in the size. To have a reliable estimate of the size, we need the object to be larger than the resolution of HST. So essentially, a radius that is larger than the full width of HST, which is about 70 parsecs, as I was saying. This is an important cut because it turns out that only 15% of the clumps are resolved, while 85% of them are smaller than this value. So when we want to study the sizes, we need to focus only on these smaller fraction of clumps, which are here. So this is not the plot that is published. I have upgraded it using the pasta markers released on the 1st of April by the pasta collaboration. So again, you can see that the clumps are much smaller now, again, 15% of the whole sample. And they're again divided in categories. So red for the disk, blue for the exaplanar, and green for the tail region. And the interesting thing is that this luminosity-size relation for the H-alpha clamp shows that all the clamps are occupying the same region. The tail clamps, which are in green, the green farfalle, are not different from the other clamps. And this is very peculiar, let's say not expected in principle, because these are clamps, again, that are formed from stripped gas, far away from the disk, embedded in the ICM, but still their properties are very similar to the clamps that are still in the disk. So we can then compare them, as I said, with samples in literature. So the black dots are clamps in isolated disks, while the blue contours is tracing the distribution of clamps in starburst galaxies. And we can see that our clamps are much more similar to those in starburst galaxies. These clamps are characterized by the enhancement not only in H-alpha, as you can clearly see, at a given size at least, but also an enhancement in the star formation rate surface density. So also our clamps most likely shows this enhancement, even if not as large as in starburst galaxies. So the idea is that similarly to mergers, the run pressure stripping is able to disturb the gas or even compress the gas, causing this enhancement in H-alpha and in star formation. Then, as I said, we wanted also to study morphology. We have some nice examples of fireballs here, at least by eye. You can see the H-alpha emission in red with a blue tail, typically pointing towards the disk. But now we have 400 complexes, so we don't want to look at them one by one, as was done in the past, because they had just a dozen of objects. We want to define some common properties to apply to all the complexes that we have. So this is the examples also that we've seen before, a bit rotated. You have the violet contour for the optical complex, and the purple contours are the UV clamps, and the gold contour is the H-alpha clamp. So we define the filling factor, for example, as the fraction of area of the optical area covered by the clamps in a certain filter, in this case the UV. And essentially, we expect the UV to cover a larger area because we are tracing a larger interval in age. And so if we have fireballs, also a larger interval in space. While the geometric center displacement is essentially the distance from the geometric center of the complex from the center of the brightest UV clamp and the H-alpha clamp. Of course, if we have only one clamp, there is no doubt. And here we expect to have a larger displacement for the H-alpha, again, because we are tracing only the very young stars that should be forming only on the very side of the complex. So if we look at the cumulative distribution of these two quantities, you can see, again, in golden the H-alpha and in purple the UV, that the H-alpha clamps are characterized by smaller filling factors. 95% of them have a filling factor that is smaller than 0.4, so can cover only less than 40% of the complex. While in UV, we can reach also values that are 0.65, so as expected from the fireball configuration. And also in the displacement, as expected, the situation is what? The H-alpha the H-alpha clamps are characterized by a larger displacement than the UV clamps, about 100 parsecs as a median value. And again, this is expected, but to have the confirmation of the presence of fireballs, we have studied the correlation of the displacement with the area of the complex and the axial ratio, elongated complexes on the left. So essentially, the H-alpha displacement is always larger than the UV one, but when we look at large and elongated clumps, the displacement increases. So essentially, if we are looking at very large and elongated complexes, the clumps are not in the center of it, but systematically displaced on one side. So the case that we're seeing at the beginning is a nice case, but it's not the only case in which we can clearly see this. With this sample and with these quantities, we could give, let's say, some quantities that could show the presence of these fireballs in a systematic way. And this is important when we want to increase the sample and stop looking at them one by one. So as an ongoing work, I'm studying the mass function of the clumps. The masses and the ages are already published in this paper. You can see here an example for a UV clump. We fitted the SED, the 5 filters of HST with backpipes, and these are the best fitting spectra, with also the distribution of the outputs. This is the age, the stellar mass, the formation rate, dust extinction. So essentially we had the masses, but before doing the mass function, we need to quantify these two effects, the completeness and the discrepancy, that can affect and bias our results. The first one is essentially the fact that low mass clumps are also smaller and fainter, so more easily lost, and we need to quantify the fraction of them that statistically are lost. While the second one is essentially a test for bagpipes. We want to verify if bagpipes is able to give us reliable estimates of the masses. To do that, I built a sort of model for the clumps. So I created a morphological shape for the clumps. I stacked together resolved round clumps in the tails of our galaxies. It's essentially the sum of two Moffat functions. This is the shape. And given the mass of the clump, I can give to the shape a size, so a physical size from the mass-size relation. And given an age of the clump, I have essentially the shape of the spectrum, if the UV is very bright, if we have H-alpha, etc. And the combination of the two is giving me the mass-to-light ratio, so essentially the normalization of the spectrum. So I created this library of mock clumps of a given mass, age, and elongation. So I can compute the shape, the size, and the SED, the spectrum of the clumps. And I added them to the real images. So you can see what in each circle here, in each grid, in each square of the grid, you have a mock clump. And I rerun Astrodendro just like I did with the real clumps. So this creates, essentially, I'm putting the clumps in the very same conditions in which I am detecting also the real clumps, crowding, background, etc. Some clumps will be lost, and kind of lost, and essentially this is the completeness, and quantifying the completeness of the sample, while the clumps that are redetected can be re-studied with bagpipes, and I can compare the output mass with the input mass that I know a priori. And these are the two results. So, for example, for the H-alpha tail clumps, in this case, this is the completeness. As expected, at high mass, we can observe all the clumps that are there, while at low mass, we lose them more and more. And we cut the sample at 50%. While here, you have essentially for all the clumps that were, the mock clumps that were reobserved, on the x-axis, the results by bagpipes, so the observed mass, and on the y-axis, the input mass that I gave to the clump. And you can see that this is the one-to-one relation. And at high masses, there is a good agreement, while at low masses, there is a little discrepancy in which the observed mass is systematically smaller. But essentially, that's why we wanted to do that. And so the idea essentially is that for each clump of which we have an observed mass, for example, this red strip, this red line, we have a Gaussian distribution in which we have the interval of possible input masses, intrinsic masses of the clumps. So we are able essentially to recover the intrinsic mass of the clumps. The fitting to the mass function is done in a Bayesian way, so without going, let's say, without looking at the whole formula, but I just want to point out the presence of these three main parameters, these three main components, which are the mass function with the slope alpha, the discrepancy that I was talking about, so essentially the distribution of intrinsic masses given the observed mass of a real clump, and the completeness of the sample in that bin of input mass. So these are, for example, the results in details, which are quite, let's say, I'm quite confident about these results right now. So for the H alpha, it's very interesting because the slope is consistent with 2. So as I was saying at the beginning, with a scenario in which the clumps are still forming following the turbulent cascade, again, even if they are formed from stripped gas, far from the disk, embedded in the ICM. So it seems to be a very robust mechanism. In UV, there is a steepening, the slope is larger, and also this is predicted by some models to at least observe a steeper UV slope, because we are tracing older clumps that had time to evolve, evaporate, merge, etc. These are some preliminary results for the extraplanar and disk regions, H alpha UV, H alpha UV. It's still a bit more difficult in these regions because we have the underlying disk with the old population that is, let's say, not easy. It's not easy to separate and discriminate from the young population of clumps. And but even if the slopes in H alpha seems to be larger than expected, there is still the trend for which the UV is steeper. So this trend is recovered, and of course, we are still working on that. To give a summary and then I conclude, we released the first statistically relevant sample of clumps in these kind of galaxies, the RAM pressure stripped galaxies. We have shown that RAM pressure stripping seems to be able to enhance the star formation in clumps. So the clumps are compact and very bright in H alpha, and they're forming a lot of stars compared to those in isolated disks. The environment seems to have little effect, at least from the observable that we have studied in the clumps, because they are similar to the clumps in the disk, and they are also forming in the same way the turbulent cascade that we observe in isolated disks, but also in irregular galaxies, starburst galaxies. And finally, given some quantities, we were able to find evidence of fireballs in the tails without looking at the complexes one by one. It's important not only to, let's say, clearly state that there is this kind of morphology, but also to study the fate of these objects, because it's important to understand how the stars are distributed if we want to model the potential of these objects and understand if they remain self-gravitating, bound to the galaxy, or not, because maybe the tidal field of the galaxy can disrupt them, or they can survive, escape the galaxy, and forming a sort of small population of dwarf galaxies in clusters completely dark matter free, which would be quite interesting. And there are also some observations, let's say a couple of cases of this kind of objects. So thank you for the attention, and